Hey, welcome back to Math with Patrick. It's June 15th, and we're solving problem number 166 from the Daily Epsilon calendar. And let's try to figure out why today's answer should be 15. So we have three different variables, a, b, and c. They all have these logarithmic expressions attached to them. And when we plug in the right values for a, b, and c, do all this arithmetic, and finally raise it to the power of -1, we should get 15. A few things that I initially notice, none of these logarithmic expressions are going to be like integers or whole numbers, right? Because this is asking like, what power can I raise 2 to get 3? So this is like 2 to the power of something is 3, and this number right here is going to be this exponent. And there really isn't a whole number to get 2 to some power to get to 3, because 2 to the 1 is 2, 2 to the 4 is, 2 to the 2 is 4. And so this mystery exponent is somewhere between 1 and 2. It's not 1/2. And I don't really know what it is, like super specifically, but it's not going to be a whole number. And the same issue is happening here, where I don't really know, like 8 to some power equals 6. Like this has got to be now less than 1 and above 0. So I can get like a ballpark value of how big a, b, and c are, but I don't really know for sure. Something kind of interesting, all of the arguments of the logarithms are multiples of 3. Maybe that's going to matter. All of the bases of the logarithms are powers of 2. Maybe that's going to matter. And then ultimately, once we do all this arithmetic and plug stuff in, this last like power of -1 is just going to flip our number on the inside. And so like if we did like 2/3 to the power of -1, that's going to be the same thing as 3/2. So ultimately, I'm hoping that we were going to get 1/15 on the inside of the parentheses there. Now, I don't really know where to start besides just plugging stuff in. Like, I don't really see much being simplified on the inside there. Maybe I could multiply the denominators, I guess. But maybe there's a reason why it's written as two separate fractions. And so I'll keep it separate for now. So just plugging stuff in, I get 3 times log base 8 of 6 minus 1 over 3 times log base 2 of 3. And then we're going to multiply this fraction by another one. 5c is going to be 5 times log base 32 of 12 minus 2 over 5 times log base 2 of 3. And I'm just going to omit that power of -1. We both know that the thing on the screen should be 1/15. Okay, one log rule I could use is anytime you have some kind of coefficient out front, it could also be written as a power. And so maybe it would be nice to condense some of these numbers. So I could do like log base 8 of 6 cubed, which is 216. And then I'm going to have that -1 on top. Oh, Quill just joined me. And I could do the same thing in the denominators. I could do log base 2 of 3 cubed, which is 27. And I'll do something similar over in this denominator, where I'll have log base 2 of 3 to the power of 5, which is 243. Honestly, this is not looking so hot, especially here where I start gonna, like, with this 5 and this 12, if I keep going with my pattern, I don't really know what 12 to the power of 5 is off the top of my head. And so with these numbers getting really, really big, I don't feel like this is the right way to do it. So just direct substitution, I'm not really seeing a good endpoint for getting 1/15 out of this. So maybe we should start thinking about how each of the logarithms have this base that's a power of 2. So here I could rewrite the logarithmic equation as 2 to the power of a equals 3. I could do this as 8 to the power of b equals 6, and then 32 to the power of c equals 12. And oftentimes, finding a common base is a good solution, or a good step rather, in logarithmic or exponential equations. And so this first equation is going to look the same because the base is a 2, but I can force this 8 to be a 2 cubed, to the power of b. And then anytime that you have stacked exponents, you can just multiply them like this. So I'll do 2 to the power of 3b equals 6, and then 2 to the power of 5c equals 12. And I'm noticing that I have a 3b and a 5c already in the original expression. So maybe if I do something like 2 to the power of 3b minus 1 and 2 to the power of 5c minus 2, maybe something cool will happen from here. I'm still not quite sure yet. Anytime you have a difference in a exponent or an exponent, you can rewrite it as a fraction. So this is going to be 2 to the power of 3b over 2 to the 1, but that's just 2, so I'll just do this. And then likewise over here, I'm going to get 2 to the power of 5c over 2 to the power of 2, which is just 4. And so these expressions here could be, well, let's see, this is just the number 6 from here. So I could say that this is going to be equal to 3, right? That's 6 over 2. And then likewise, this number over here is going to be 12 over 4. So that yet again is another 3. And I just figured it out. Okay, so see how we got 2 to some power, like 2 to 3b minus 1 is equal to 3, and 2 to the power of 5c minus 2 is equal to 3? Well, maybe this is familiar because it lines up with our first equation. 2 to the power of a is equal to 3. And so these exponents all have to be equal to each other. And so I'll write that here in red just to kind of like let it pop out, that a is equal to 3b minus 1, and it's also equal to 5c minus 2. These are all the same exponent. So if we play this substitution game, we're going to get a over 3a times a over 5a all to the power of negative 1. I'm substituting this for an a in the top, and likewise, same thing for the 3b minus 1. Here, it's really clear to me that all the a's cancel, and I'm left with 1/3 times 1/5 to the power of negative 1. Here is our 1/15th. And then finally, once we raise that to the power of negative 1, it flips, and we get the number 15, and that's today's date. Wow. So something about rewriting these exponential or logarithmic equations with the same base, 2, really helped out to kind of like match all of the expressions with each other. That was a really fun solution. Anyways, we found the 15 for today. That's how I solved it, and I hope you enjoyed. I'll see you tomorrow. Bye.